Sachin Paramane. So, Dr. Sachin Paramane was born in Walchan Nagar, India in 1979. He has done his diploma in mechanical engineering from Government Polytechnic, Karad in 1997, bachelor degree from Walchan College of Engineering, Sangli in 2000, MTech degree in thermal engineering from IIT Delhi in 2002, and PhD with specialization in CFD from IIT Bombay. His professional experience is he has more than 14 years of industrial experience in R&D centers of various industries. Earlier, he worked at R&D Center of CG Power Industrial Solutions Limited, Mumbai for 10 years. Engineering Research Center for Tata Motors Limited, Pune for 2 years, and R&D Center of Mahindra and Mahindra Limited, Nasik, for 1 year. Presently, he is working with Metal Power Analytical Private Limited, Mumbai as DGM R&D. His research interest includes thermal design and CFD analysis, HVAC and cooling system of. He also takes interest in development of state-of-the-art experimental facilities for validation of numerical analysis and development of for accurate prediction of thermal system performance. He is also a Bureau of Energy Efficiency Certified Energy Manager. If I talk about academic activities of our speaker today, he is a member of Board of Studies of Mechanical Engineering Department, Upper University, Patiala, Punjab, and presently at GH Raisoni College of Engineering, Nagpur. He has 7 patents, 40 international journal and conference publication to his credit, and delivers invited talk and keynote addresses in the area of computational fluid dynamics and energy efficiency improvement of thermal system at various institutes in India. Additional to this, he is also a reviewer of different scientific journals like IEEE translations on power delivery, applied thermal engineering, International Journal of Thermal Science, Energy Application of Computational Fluid Mechanics, and Journal of Power Technology. So with such a rich biodata, with such a rich background, I would like to invite Dr. Sachin Paramane. Sir, please welcome and please continue.
Thank you so much, Professor Dutt. First of all, I would like to thank AD Patel Institute of Technology, Anand, for inviting me for this STTP on Applied Computational Fluid Dynamics for Engineer. It's my pleasure to have with you all, and I would like to share my experiences, some knowledge on CFD, which I acquired during course of my academic as well as professional career. So with this warm introduction and warm welcome for the STTP, so I would like to continue with this presentation. The topic of my presentation today is computational fluid dynamics and industry. Basically, it is an application of computational fluid dynamics for the industry. I think I'm audible to you all. Is it okay?
Yes, sir.
Yeah. So outline of my today's talk is, first I would like to brief you about what is CAE, that is computer aided engineering. Then computational fluid dynamics, which is one of the part of this CAE. So in this CFD, I will just tell you about what is computational fluid dynamics, why computational fluid dynamics, and how computational fluid dynamics. So if we could get through these three questions, then at least some basics of CFD you will be able to understand. The next topic I would like to cover is CFD process, how CFD is used in the industry. I will introduce about that CFD process. Thereafter, we'll discuss about what are the CFD softwares which are available in the uh, industries and how these softwares are used by the industries. So this is nothing but CFD software landscape. Then I will take you through some of the industrial applications of CFD. So here, basically my presentation will consist of mostly animations and videos, which will uh, tell you how this CFD is useful in the industry or any other areas. So my topic will be covered through the animations and videos. Then I will touch upon the application of CFD in sports, because this is one of the emerging areas where CFD is applied successfully. But this topic is not covered anywhere in depth. So I have done some studies. So I will take you through application of CFD in sports and what are the industry expects from academia. So that also will talk. And after this, we'll have some question answer if you have any queries related to CFD or anything in the industries. So I would like to, I'll be happy to answer those queries, and that will be the end of the presentation. So I will try to cover in 1 hour 10 minutes, and then we'll have the this question answers. So first is what is CAE? Basically, CAE is a technology which is concerned with the use of computer systems to analyze CAD geometry, allowing designers to simulate and study how the product will behave so that the design can be validated, refined, and optimized. So CA is nothing but the use of computational resources, computational system to model the geometry, to analyze, simulate, and uh, understand the behavior of the product in particular conditions or particular environmental conditions or operating conditions in which this product will be used. So this is nothing but CAE. And nowadays, CA is an integral part of any product development cycle. So if you talk about any industry, CAE has become an integral part, and it plays a major role in product development cycle, where CA is applied for uh, improving the performance of the existing product or design a new product, where the design will be validated on computer, and then it will be taken for prototyping, and finally it will be launched in the market. So this is a product development cycle. You name any product where CA is used in a large scale. Then we'll see what are the areas of applications of CAE. First is a finite element analysis. So this finite element analysis is used for mostly in structural simulations, where load carrying capacity, deflection, stresses, then stresses, these are evaluated or determined using finite element analysis. Then second is the computational fluid dynamics. So this computational fluid dynamics is used to study the uh, flow of fluid over different uh, product or applications. Here, flow not only flow but heat transfer is also studied using CFD. So here there is a flow or heat transfer, CFD is applied, or it can be used for studying the behavior of the thermal system or evaluating performance of the thermal system. So these are the areas where CFD is used in the industry. Next one is a boundary element analysis. Now nowadays acoustics is one of the emerging area where we have to predict the noise level. or reduce the noise level from product or system. So in that case, this BEA, by boundary element analysis, is used, where the system is simulated using boundary element analysis, and then noise levels are predicted, sound pressure level or sound intensity. Those are the parameters which are used for the characterization of noise, and then this noise prediction is done by using boundary element analysis. Then another application of CA is basically kinematic or dynamic analysis. Here, motion study, then mechanism study of different mechanisms. So this has been this is done by using kinematic or dynamic analysis. Spring calculation, movement of different arms, then wheels, rotary objects. So these are studied using this kinematic, wall train, etc. These are studied by kinematic analysis. So these are the broad areas of application of CE. So in this presentation, I would like to touch upon one part, that is a computational fluid dynamics. So first, we need to understand what is a computational fluid dynamics. So if we see the definition in the book by Verstig and Malal Sekara, so in the book, it states that a CFD is the analysis of systems involving fluid flow, heat transfer, and associated phenomena such as chemical reactions by means of computer-based simulation. Okay, so it tells that the computer-based simulations are used to study different phenomena associated with fluid flow, heat transfer, and mass transfer. Then another definition in the book by Professor Atul Sharma, Introduction to CFD, what he states that CFD is a theoretical method of scientific and engineering investigation concerned with the development and application of video camera like a tool, which is a software which is used to analyze the fluid dynamics as well as heat and mass transfer problem in unified way. Basically, it is nothing but a software which is just like a video camera like tool which is used for studying the different phenomena associated with the fluid dynamics and heat transfer. Here the software is like a virtual video camera and results in a movie where each picture gives a fluid dynamics information, that is flow properties, which are nothing but velocity, pressure, temperature, and turbulence, kinetic energy, etc. So these are the parameters which uh, will be shown in a picture. And when we combine this picture in a sequential time-based manner, then it will create a movie, which is nothing but an animation, what we see in different CFD analysis. Now, in order to understand computational fluid, we need to have understanding of three branches of science and engineering. First is engineering fluid dynamics. We should know basic engineering fluid dynamics, different laws, fluid dynamics properties. All these things needs to be understood. Navier-Stokes equation, then the terms in those Navier-Stokes equations, those needs to be understood thoroughly in engineering fluid dynamics. Then different concepts also we need to have understanding. Second is the mathematics. Basically, mathematics is used for understanding the partial differential equation, vector algebra, vectors, and other mathematical theorems, Gauss theorem, curl, divergence. All those understanding of these concepts are necessary to understand the CFD. And third is nothing but a computer science. Computer science, I mean to say, is to solve this governing partial differential equation, we need to understand the coding language, or we need to do coding for the uh, analysis or solving this equation. So we need to have understanding of any computer coding language, be it MATLAB, C Sharp, C, Python, any computer language, Fortran, etc. So this language, understanding of this language and coding is required for the CFD analysis. This means, I mean to say, when we are developing our own code, then this is very much required. And next is why use computational fluid dynamics, or who are the uh, users who need this CFD. First is the architects. So architects use CFD analysis to design better ventilated buildings. So you need to understand the airflow distribution inside rooms, or ventilation, how it will be carried out. Then if he has to design the theater or a clubhouse or any um, a particular hospitals or anything, any building, then he needs to understand the flow distribution and ventilation system. So he will use CFD for analyzing this and designing or modifying their design according to requirement of the comfort level inside the building. Then next is the designer of vehicles. As you know, CFD is widely used for aerodynamic uh, profile or aerodynamic design of the vehicle, exterior of the vehicles, where drag should be minimum, and there should be aesthetically better design of the vehicle. So this is one of the application of the CFD for vehicle. I will tell you in detail about the coming slides how CFD is used in the automotive industry. Next, in engineering, chemical engineers use CFD to understand the mass transfer phenomena or effect of mixing of different chemicals, and to understand the properties. This CFD is used for the chemical engineer. Then petroleum engineers, they use CFD to get maximum yield of excavation of petrol from the earth. Uh, so to design the excavation systems, then how these petroleum products are carried to the ground from the deep level. So for designing of those systems, CFD is used for the petrol is used by the petroleum engineer. Next is surgeons. Nowadays CFD is again widely used in biomedical application. So based on the blood flow in the arteries, heart, or any other organ, a surgeon will be able to determine its operating procedure, or how he can carry out surgery. Then he can also understand the development of any disease uh, in the patient. So this can be predicted, and it can be successfully used for the biomedical application. Then meteorologist, basically a meteorologist is using this UD for predicting the weather or weather forecasting. Nowadays, there is large improvement in the weather forecasting because of use of CFD. So they will be able to tell the movement of cyclones, then direction of cyclones, their intensity. Then if rain forecasting is also predicted using CFD. Then climate change, low pressure regions in the sea, etc. These are CFD is useful for meteorologists for prediction of this application. Then safety experts. This is nothing but smoke visualization. If there is a fire inside any tunnel or any building, then how this fire can be extinguished, or how this smoke can be uh, taken away from those tunnels very easily. So for designing of those uh, fire equipment or ventilation system in the tunnels, the CFD is used. Then military organizations are also now using CFD for developing and designing better equipment, better arms. Then in sports, as you may be knowing, CFD is again now widely used in the sports for badminton or cycling. How this airflow over cyclist takes place. Then in football, cricket, also this CFD is used. Then this is CFD practitioners. They use the CFD to show the colorful pictures to the clients and get good amount of money from them. So they can convince those clients with these colorful pictures and animations. So they are using this CFD. Now, next is if we compare experiment versus simulations. So basically, first point you have to understand is, as a rule, CFD does not replace the measurements completely, but the amount of experimentation and prototyping and the overall cost can be significantly reduced. So if we plan to do experiments on different prototypes, then we have to make many number of prototypes. But here we can avoid that prototyping by creating different scenarios in different our CFD simulations and study phenomena accordingly. So in experiments, quantitative description of flow using measurements is carried out, whereas in simulation, quantitative description of flow using CFD software. Now, in experiments, one quantity is measured at a time. That means number of sensors will determine the number of locations where we can measure the quantity. But in simulation, we can know all desired properties at any location inside the computational domain. Then experiments are limited by number of points and time instance, whereas in simulation we can do very high resolution simulation and determine any quantity at any location and at any instant of time. Then experiments are expensive. Expensive in the sense we need to have laboratory, then infrastructure, resources, manpower, electricity, measuring equipment. Cost of sensors is also very high. So all those things are required in the experiments, and it is also limited by number of hours we can continue. That means if we have one shift, then only 8 hours are useful for the performing the experiments. But in simulation, you can run the simulations overnight and still you will get the result. So it is basically cheaper, except the cost of the licenses, which are very expensive in case of CFD. Then experiments are slow, whereas simulations are faster. Experiments can be done sequentially. That means one experiment or one experiment is done for studying one phenomena. Then next phenomenon will be done after completion of the first experiment. Whereas simulation, you can run the simulations on different machines, and this is a parallel operation, and you can save a lot of time for the product development. Experiments are single purpose, whereas simulations are multiple purpose. So many objectives can be met using the simulations. Is it okay? Hello?
Yes, sir.
Okay, yeah. So
Yes,
I think my pace is okay now.
yes, sir. Yes, sir. It is fine.
Yeah. So now next part is CFD process. How this CFD is applied for the analysis. So basically, there are four steps in the CFD analysis. First is the geometry creation. This is nothing but whatever phenomena we want to analyze or study, we need to define the computational domain and create a geometry of to analyze the particular phenomena or product. Second is the pre-processing. Now, pre-processing is nothing but we need to divide this computational domain into small elements, which are called as cells or control volumes or nodes. And then this process of converting computational domain into small control volume is called as a meshing. So pre-processing is nothing but meshing and applying the boundary condition. That is, what are the boundary conditions this phenomena is required. So that comes into the pre-processing part. Third part is the solver. That means here we actually solve those governing equations using the software, and then finally is our post-processing. Post-processing is nothing but the analysis of result. Now, the analysis of the results can be done in a two way. First is a qualitative analysis, and second is a quantitative analysis. In qualitative analysis, we just show the flow distribution, streamlines, velocity vectors, temperature distribution using colorful pictures or color maps. So that is called as qualitative analysis. And in quantitative analysis, we determine the quantitative values like pressure drop, or heat transfer rate, heat transfer coefficient, drag coefficient, lift coefficient. So these are the parameters which are calculated, and that is called as a quantitative analysis. Now, next topic is landscape of CFD software. That means what are the CFD simulation software which are available in the market, and how different industries are using this software. So, usage of CFD, if we talk about industry-wise, then automotive consists of largest user of the CFD simulation, which is around 20%. Then next is engineering services, consultancy and services industries. They are using around 18%. Consumer products using 10%. Energy industries, power industries, they are using around 10% license, 10% application. Then aerospace is 9%. Industrial machinery is 9%. Then electronics industry is also widely using this CFD for developing the their product or making it compact. I'll talk about this electronics application in the coming in next few slides. Then in marine application, then there are medical and pharmaceutical industries are also using CFDs basically for drug delivery or making those drugs capsules. So there these pharmaceutical and medical industries are using CFD. Then we have water and wastewater management where CFD is again used. So next is which are the softwares presently used by the industry. So if we talk about CFD landscape, then there are three major companies which dominate the market share of CFD. First is Siemens, uh, first is ANSYS, second is Siemens, and third is OpenFOAM. Now, if we see ANSYS is around 26%, whereas Siemens they are using it is about 20%. Now, ANSYS you may be knowing Fluent, Star CFD, Fluent, CFX. These are the CFD softwares from the ANSYS, and in Siemens they are Star CD and Star CCM. These are the Siemens, and third is the OpenFOAM. This is nothing but open source software, which is again widely used by the mm, industry. However, for OpenFOAM, we need to have very strong understanding of programming and also basic understanding of engineering and mathematics. So this is basically nothing but the programming type of software. There is no GUI as such in the open form, and we have to give all those input using coding or programming. Whereas ANSYS and Siemens they have graphical user interface, so we don't have to bother about many of the parts uh, in basically meshing and solving. All those GUIs are available. Then there are other softwares as well in this for the CFD analysis, like AVL, Convergent Science, Dassault Systems. Then we have SolidWorks, Autodesk. COMSOL is also one of the software which is widely used by the industry people. So this is one of the basic landscape of the CFD. Now, if we talk about CFD software workflow, then as explained in the earlier slide, we have pre-processing, meshing, and post-processing. Now, pre-processing is nothing but 3D CAD import, cleanup, and use of CFD embedded geometry creation. Like if we take example of ANSYS, they have 3D space CAD as a preprocessor, so it is inbuilt. So that is CFD integrated. Then in meshing also they have ICM or fluent meshing, so it is also integrated in the ANSYS. And they have solving and processing, which is again integrated. So users are preferring CFD integrated preprocessor mesher as well as post-process. So you can see 47% pre-processing, 82% meshing, and 74% post-processing, which is already integrated in the CFD software, and those are widely used by the uh, users in the industry. Then there are standalone software which are developed for that particular application. like AutoCAD or Creo. Those are used developed for CAD geometry or CAD modeling. If we talk about meshing, then there are some software like Pointwise, Snappy, XMesh. Those are developed only for the meshing purpose. And third is a post processing, like we have ParaView, Insight, TechPlot. So these are the softwares which are developed for the only for post processing. So people will combine these softwares or will use this software individually and then use the CFD process individually. Like they will generate CAD geometry in Creo, and it will be imported in the point wise where meshing will be done, and then that mesh is they can import in other solver, and then export that export the results for post processing in different post processors like ParaView or TextPlot. So these are the this is basically CFD work software's workflow which is used in the industry. Now, after giving some introduction and usage of softwares for CFD analysis, I will take you through some of the industrial applications of computational fluid dynamics. First, I will talk about the automotive application. Now, CFD in automotive application is used in two broad areas: powertrain and non-powertrain. Powertrain is nothing but engine and transmission system. Engine to transmission system is called as a powertrain, and other than this powertrain, rest of the things are non-powertrain application. Now, first application of CFD is for external aerodynamics. That means to determine the shape of the vehicle, car, to reduce the drag coefficient and to improve the fuel economy. This external aerodynamics means CFD is used to understand to study the external aerodynamics of the vehicle. The next is a passenger comfort. Now there is a heating HVAC system which is there in every car. HVAC is nothing but heating, ventilation, air, and air conditioning. So every passenger or every person inside the car should feel comfortable when air conditioning is switched on. So this automotive manufacturer, they are using CFD to understand the airflow distribution inside the car. That means whether air from the louvers is reaching to each passenger, and there is a comfort level achieved in the vehicle with minimum time. So to design the air conditioning system, this CFD is used. Next is de-icing and defogging. In winter area very low temperature areas, there is a icing or fogging taking place over the windshield, and there is a criteria. That means within this much amount of time, this fog should get cleared when you switch on the heating system. So there this automotive manufacturer, they are using this CFD to understand the this transient phenomena. Then HVAC ducts, as we have already seen. Then fans, heat exchangers, that is nothing but fan and radiators for the engine cooling system, front end flow. Then lighting. Now headlamps and tail lamps. For design of the headlamp and tail lamps, CFD is used because these headlamps and tail lamps generate the heat, and that heat needs to be dissipated effectively. So for design of that lighting system, CFD is used. Then under hood, thermal modeling. That means whatever heat is generated from the radiator, it should not dissipate inside the cabin. So there are certain criteria. Again, the exhaust from the bottom of the vehicle, it should not dissipate heat inside the passenger. Otherwise, there will be heating inside the compartment. So there, CFD is used. Brake cooling, hydraulics, airbags inflation, then fuel filling and supply. There also CFD is used. Then wind noise prediction. For prediction of noise, air cutting noise, the CFD is used by the automotive manufacturer. Then for powertrain application, if we consider the the airflow in the inlet manifold and exhaust manifold. To design those inlet manifold and exhaust manifold, CFD is used. Wall flow, that means how this air is taking place inside the car. Okay. So there is it is used in that CFD analysis is used in the engine compartment intake manifold. Then we have pump for water flow and jacket cooling, air intake system, torque converter, clutches, transmission, exhaust after treatment, and mufflers. So these are the areas where CFD is used in the powertrain application. Now I will take you through some of the external aerodynamics for the experimental. How the experiments are performed in the wind tunnel to understand the airflow over the car. So this is an example of Mercedes car where flow visualization is used to uh, check any vortices or wake which is happening behind the car. That is, it can be studied using the flow visualization. So here, these are the guns which will provide the smoke, and then any attachment separation points. Uh, those are studied using this flow external aerodynamics. You can see how the flow is taking place over the car at different engine speed or vehicle speed. So there should be smooth profile of the car. We have a lower drag coefficient. Then design of spoiler. When the spoiler is placed behind the car, how it will affect the aerodynamics. That can be studied using the experimental wind tunnel. That can be studied in the wind tunnel. So you can see how flow is happening over the car spoiler. Then rear profile, uh, then you have underhood profile, how there should be smooth transition of the curvature. Okay, so this is one of the example of experiments in the wind tunnel for determining the shape of the car. Then this is one of the example of how CFD is used for external aerodynamics for trucks and buses. So this is a MAN truck. So you can.
The greater the front surface and the more edges a body has, the greater its air resistance.
So because of this box-shaped front area, there is a large air resistance.
Found in birds, for example, is ideal.
So if the shape is modified according to aerodynamic shape, then it will reduce the drag.
Resistance. Doubling the speed results in a fourfold increase in air resistance. Thus, at a speed of 85 kilometers per hour, 40% of the overall resistance is already generated through air resistance alone.
So as the speed increases, there is a fourfold increase in the drag coefficient.
Rounded edges at the front.
Now, how this CFD is used to modify the box shape design to reduce the drag.
Therefore, the air resistance. The aerodynamic potential that can be achieved without taking into consideration legal framework conditions is demonstrated by an example of the MAN Concept S future development.
So you can see this just by changing the shape of the truck.
The key features
there is a lot of reduction
adaptation of the tractor machine and semi-trailer as a single unit, the aerodynamically ideal shape.
You can see the difference
Reduction
between
of
these
the back
two
pressure on the front of the vehicle.
Pictures.
Extensive side and underbody paneling. Protruding components are minimized. For example, the mirror is replaced by a camera.
So here mirror has been replaced by camera because the mirror also acts as a
through optimization
resistance.
Of the cab shape, it has been possible to reduce the air resistance for the TGX by around 4% compared with the previous TGA model.
So just providing here roof spoiler,
adjustment of the spoiler
there is a lot
to lower
of
the increase in drag in this area. In the further process, the side contour of the semi-trailer and the cab front in particular offer potential for reductions.
Then there is a modified design of the bumpers,
such as tipper troughs, supporters, 50.
Okay, so this is a way how CFD is used for the external aerodynamics. Then we have another example how vorticity, we can use the visualization, flow visualizations to study the better aerodynamic cars or concepts cars. So this is just the vorticity contours over a car, and you can see the picture how these are used for the better design of the vehicles. Then we can see passenger comfort, that is inside cabin, how airflow distribution is happening through the air conditioning louvers. You can see whether this designer can study whether the air is reaching each passenger using CFD analysis, and then they can develop the air. Means they can decide on the airflow as well as location of these louvers on the dashboard. Then for internal combustion engine, CFD is used for the study of the intake manifold and exhaust manifold. So these are the cold flow simulation. That means how air fuel mixture is taken inside the combustion chamber. So this is a velocity magnitude. That means how this when piston movement happens, how this mixture is taken inside and then it is exhausted through the exhaust manifold. So this will help in better design of wall timing as well as combustion chamber design, location of the walls. So this can be optimized using CFD. Then apart from this, we have other application like engine cooling jacket simulation, under hood thermal management, then Formula One car external aerodynamics and climate control studies. These are the applications of CFD in automotive industries. Now, how the CFD is used in the electronics industry. This is the CFD is basically used for better heat dissipation from the electronics circuit. Nowadays, as our requirements are going up, power, there is a lot of heat dissipation in the circuits. Circuits are becoming smaller, whereas heat dissipation requirements are increasing day by day. So to dissipate this heat very effectively, we need to have heat sink, very better design of heat sinks, then heat pipes. So these are the products which are useful for dissipating the heat from the electronics component. So in order to optimize this heatsink design and fan design in the electronic circuit, this is CFD is used. So this is one of the examples of CFD is helpful for designing the electronic component. So this is an electronic enclosure, and then different components which are generating the heat are modeled, and then fan locations, fan flow, etc. all are defined using boundary conditions. Then meshing is done, and then simulations are performed to determine. These are the mesh for the electronic component, and this is how airflow distribution occurs over different components, and how heat is collected from the these components by the air, and then it is dissipated in the cooling. Now placement of this component and optimization of different cases, we can use CFD, and we can optimize and select best design which is useful for that particular application. So different scenarios can be studied on computer and using CFD analysis, and we can select the best scenario which will help the better heat dissipation. So these are the applications of CFD in industry. Enclosure design, flow design, fan placement. So these are the areas: fan sizing, airflow optimization, then enclosure design. So this is where CFD is used in the electronics industry. Then, as you may be knowing, pump industries again to determine the performance curves of pumps or fans, we can use CFD because uh, every time we cannot do the experiments. Suppose if we design higher capacity pumps and we don't have the experimental facility in house to test those pumps, then here we can use CFD analysis to uh, evaluate the performance of the pump, or to design the volute, impeller, casing. All those designs can be done, and then performance can be checked using CFD analysis, and best possible design can be used for the actual prototype and supply. Then there are some examples of renewable energy, how this EFD is useful in the renewable energy areas. Now we'll just see the example of wind turbine. Now renewable energy is getting a lot of focus by the government, whether it is solar or wind energy. Then different wind parks are being developed across India. Now we need to understand when we will get the maximum amount of energy with the wind, such that the location of wind turbines are optimized. That means if we optimize the location, we can get the maximum amount of energy from the wind turbine without affecting the performance. So these are some of the this is one example how we use it. So this is a wind turbine for 2.3 megawatt power plant onshore. So it has a diameter of around 80 meter, and height is 80 meter. The center of the wind turbine is at 80 meter, and analysis CFD analysis performed over the wind turbine. So this is the magnitude vortices which are formed uh, when the wind turbine rotates. Now we can place the wind turbine which is not within this vortices region, and this will give us the proper location of different wind turbines, and we can get the maximum yield from the wind turbine. Then there is a design of blades which will give us a better aerodynamic profile of the blades, and that will give us the lower drag coefficient, and will have a higher energy output from the wind turbines. And this is another example how CFD is used to study the wake dynamics behind those wind turbines. So you can place the next wind turbine where the wakes are minimized. Then CFD is again used in the building design, designing of the cities, to understand the existing building design, how the airflow will occur over the buildings, and is there any harm for the structural design of the building if there is a cyclones or very high velocity wind blowing over the buildings. Then I was explaining about the biomedical application. So to understand the blood flow inside the arteries and veins, the CFD is used. So just this is one of the example of blood flow in artery. So you can see the left is a healthy artery, and there is a progression of disease in the artery, which is 30% as seen from the right animation. Then there is increase in the disease progression, which is now 60%. So there is a blockage of the vein, which can be seen. Then if there is a 80% blockage, the blood flow can be seen. And then depending upon the progression of the disease, these surgeons, medical surgeons can determine when to operate the patient, and the operations can be planned accordingly. So this can also be studied using CFD. Now, in nature, you can see the direct applications of CFD, like bird flow, geese flow, bird flow. Then swimming of the fish inside lake or in the water. So they will bird will fly, or this fish will swim in a particular way in a group, so that the next fish will have lesser amount of drag, or they have to utilize their minimum energy to swim in the water. Now this is one of the animation of fish which are swimming in the water. Now you can see that these two fishes which are behind the front fish, they will try to go in the wake which is generated by the front fish. So they will try to go in the wake which is generated by front fish, so that they will have to use less energy to cover the distance or to swim in the water. So this is one of the high performing simulations which was done by university from Sweden, I think. So they have done this simulation in supercomputer for many days, and then they have published this animations and research papers. Okay. Now, next topic is CFD in sports. So CFD again is used in the sports. Just I would like to give some of the example of how this CFD is used in the sport. So this is a soccer ball or football, and depending upon the flight of this football, it will take a particular direction depending upon the resistance. So this is nothing but a flow over sphere, and this is a wake which is found behind this football, and due to pressure difference at front and back, then it will take a particular path, and this path is used to uh, divert from the defender, and then a goal can be scored. So this is the idea behind the studying the flow dynamics over the football. Now you might have seen some of the famous free kicks. Basically, I will just show you about the free kick by Beckham against Greece. So you can understand how ball moves past these defenders, and then goal is scored due to this typical uh, path of the ball. You can see the video. So there is a curved movement of the football, you can see, and the goal is scored. So this is a way how they use the understanding to uh, uh, make use of these free kicks to score the goal. Next one is from Roberto Carlos of Brazil, who has scored the goal against the France. This is one of the again famous free kick. From long distance, he has scored this goal, and there is no movement of goalkeeper, no large movement of the goalkeeper, even from such a long distance. See the movement of the ball. So there is complete curved. He has hit the kick in the right side, and then ball has moved towards the left side. So there has been a case study again how goal has been scored from such a long distance, and how he has understood this flow dynamics or physics. Then another application is to understand the flow over the cyclist. When he pedals the bicycle, then how there is airflow distribution over the person. Now you can see the cyclists are using aerodynamic profile helmets. So these are used to reduce the drag and to reduce the energy required to move forward. So this is a simulation how it has been used. Now I just forgot CFD is again used for in the COVID situation. You might have gone through some newspaper how when we sneeze, how the sneeze particles spreads. So what should be the minimum distance between two people so that even if person sneezes, then this COVID virus cannot cannot reach to the person. So these are some of the simulations which has been recently performed to understand the safe distance in the COVID situation. Then the flight of traditional feather cock, pressure distribution of over the feather cock is studied. Then to reduce the effort required for swimming by the person, the swimming cap has been designed in an aerodynamic way so that it will stick to the head of the person, and then he will have to utilize less efforts to swim. Then there are in cycling race, you might have seen that the person behind will try to go in the wake which is created by the person in front of him, so that he will have to use less efforts. So these are the ways how people try to go behind the person which is running or swimming or cycling in front of him, so that he can utilize his energy for the last miles. Now I will take you through fluid dynamics in the cricket. This is nothing but application of fluid dynamics in cricket. That means to understand the reverse swing. I think many of us are following cricket, but we follow just like that. Just like it, that means we know how cricket is played. But if we try to go deeply inside some of the phenomena, then I think you will really enjoy watching the cricket in a more meaningful manner. Now, I want you to understand, or I will like to introduce the concept of swing bowling. Some of you might be knowing this, but I will explain in a different manner, or will go slightly deeper into the swing. Now, swing bowling is a skill in the cricket that bowlers use to get batsmen out. So this is the simple meaning of swing bowling. Swing bowling. Now, it involves bowling a ball in a such a way that it curves or swings in the air. And the process that causes this ball to swing can be explained through aerodynamics. Now, there are two type of swing bowling a bowler can bowl. One is the outswing and another is the in swing. Now, if we consider right hand batsman who is standing over here. Now, when bowler bowls from non-striker end, and when ball goes inside the wicket, it is called as an in-swinger. And when ball moves away from the bowler or away from the wicket, it is called as an outswinger. Now there are certain factors which determines this swing action, swing bowling. First is a seam. This is called as a seam of a ball. Now ball is made up of cork layers, and then it is sewed using this seam. So there are seven uh, stitches which are used for making the seam. The next factor which governs the swing bowling is asymmetry in the ball due to uneven tear. I will come to that point in the coming slide. Third is a speed. That means at what speed bowler is bowling. And fourth is a bowling action. Now, to understand the flow dynamics over a cricket ball, first we'll just understand the flow over a sphere. So if you see the flow over a sphere, there is a boundary layer which is formed over the uh, sphere, and there is a separation which is happening at this separation point over the sphere, and a wake is formed behind the uh, sphere after the separation point. So this is a wake region, and this wake is created by separating boundary layer as it accelerates through the surface, as it is accelerated off the surface of the sphere. And now by Newton's third law, this wake will cause an equal and opposite force on the sphere. Now, what happens when bowler um, bowls the swing bowling? Now you can see outswing bowling. So this seam position is away from the batsman, and when bowler bowls in this way, then ball will move away from the batsman. And in swinger is the seam position is towards the batsman. Now when bowler bowls, ball will move towards the batsman or towards the stumps. So this is called as a outswinger and in-swinger. Now it involves bowling a new cricket ball with seam upright at slight angle in the direction you wish to bowl the ball to swing. Now if I am bowler and if I want to bowl away from the batsman, and if I have new ball, then I will keep this seam position away from the batsman. So this is a new uh, bowling by using new ball. Now you might have also noticed that some of the bowlers, they will hide the seam position. They will put their finger on the seam so that batsman will not make out the seam position, and he will not understand where the bowler is going to bowl the ball. Okay, so this is the way how they try to avoid the uh, seam position so that it is not visible to the batsman. Now what happens when the ball is bowled? The seam trips one side of the airflow into the turbulence, and other side of the ball remains laminar. So because of this seam, there is a turbulent flow on one side and laminar flow on the other side. Now laminar airflow will reach zero velocity much quicker than turbulent airflow, and which results in asymmetry in the position of the separation points. So due to this, as laminar flow reaches quickly and turbulent flow reaches zero velocity slightly later, there is asymmetry in the uh, position of this separation point. And by Newton's third law, wake will apply an equal and opposite force on the cricket ball, causing the ball to swing in the direction the seam is pointing. Okay, so because of this, uh, ball will swing in a seam uh, in the direction of the seam which is pointing. That means this side, and towards the rougher side of the ball. Okay, so the ball swing action will take place in this way. Now, shining of the ball. You might have seen fielders. They will be rubbing the balls on their trousers. You might have seen this in the Test cricket. So what happens is you will often see the fielders constantly shining one side of the ball by rubbing it on their trousers. So what happens when they rub the ball on the trouser? They are making one side of the ball smooth. So this rubbing helps to maintain the smooth, shiny side, while the opposite side of the ball is left to normal wear and tear. That means they are making one side smooth and another side rough. So because of earlier fluid dynamics, that means roughest ball will turn towards the roughest side of the ball. So in simple terms, the aerodynamics of bowling means the shiny side travels faster through the air, while the rough side acts as a brake, pushing the ball in that direction. So this is the way how they will try to make the shiny surface on one side and rough surface on the other side. Now there was recently around 2 years back, there was a ban on two Australian cricketers, three Australian cricketers, mainly Smith and Warner. What they uh, what they have done is they have used emery paper to make one side of the ball rough. They have hidden the emery paper and they caught while rubbing that emery paper on one side of the ball, so that it will help the bowler for swinging, to make the swinging action, and the ball will help uh, to generate the swing, and then it will help to the team. But in the cricket, it is not allowed. You cannot use external things to make the ball rough. Okay. Uh, in earlier days, these Pakistani bowlers, they used to throw the balls on the boundaries, so that ball will get rough on one side. So that was also the case. Now, what happens in the reverse swing? In the reverse swing, even the seam direction is like this, is left side, but still the ball will move on the right side. So this is another way. That means we will expect that ball will move away from the batsman, but actually it will go inside, even though seam position is this way. So here, sometimes entire cricket series have been decided by the ability of team to get an older ball to reverse swing. That means older ball is used to reverse swing, where a bowler can approach with the same bowling action, but get the ball to move in a completely opposite direction. Okay. So difference between conventional and reverse swing lie in difference in flow separation on each side of the ball for the same position as the ball deteriorates during the game. Now I'll explain how it is done. So this is a bowling by Simon Jones. He bowled Clark in Ashes 2005 in the third test. You can see how he has bowled and reverse swing. Okay. Now I'll just pause. Here you can see the position of seam and how ball move inside the towards the batsman. Reverse swing. You can see now this is the seam position, and the seam is pointing away from the batsman. That means batsman will expect that ball will move uh, away from him, but actually when ball is bowled, it goes inside the stumps, and then the wicket is taken. So this is the way how some of the bowlers will use the reverse swing effectively to get the batsman out. Same video. Okay, so this is where how this swing is used. Now there are advantages and disadvantages of this knowledge. Basically, bowlers can now bowl in a certain ways that maximize the amount of swing they can get, such as bowling at a certain speed range and at a certain seam angle. Then coaches can now look for bowlers that naturally bowl in ways that cause the ball to swing. Then people may manipulate the ball in order to get more swing. This could include pinching the seam with fingernails in order to make it more prominent, causing the airflow to be more turbulent over it. Now, we have observed that this cricketers use the saliva on the ball. That saliva is used to make the shiny surface or to make the laminar flow or smooth surface only on one side. So now, due to COVID, it is banned. But earlier, the saliva was used to make the shiny surface, so that was allowed, I think. This is on now pinching with fingernails or using nails. It is not allowed. This is unethical and is a concern in the game of cricket. Now, as bowlers know how swing bowling works, it will lead to more bowlers using it and ultimately lower scoring cricket games. And this is negative as low scoring games will attract less people to the game. So cricket is a gentleman's game. Play the game in the right fairness and sportsmanship. Now another quote I would like to share it with you. Uh, a theory is something nobody believes except the person proposing the theory, and experiments are something everybody believes except the person doing the experiment, from the Albert Einstein. Basically, what he meant to say is whenever we do some numerical analysis of CFD simulation, we should make people to believe in our result. So we have to follow certain methodologies, some understanding of the boundary condition, mesh independent study, domain independent study, time independent study. So these are the studies which need to be done so that people should believe in our results or theory which we are proposing using simulations. Now I'm coming towards the end of the slides or presentation. So there are certain expectations from the industry, from the new uh, young generation people who are joining the industry after passing out from the colleges. So whatever project or whatever work they do, there are three aspects. That means the at least one of these aspects should be met. First is whatever project or whatever work they are doing, whether it is reducing the cost in any way by means of process, material, or design. So if it is reducing the cost, industry will go for it. Then whether it is improving the quality or reliability of the product, if certain work they are doing, certain process they are proposing, so that should improve the quality and reliability of the product. And third is time. That means time required for manufacturing or assembly or any process. If it is reducing, then there is a way forward to implement that idea in the production system. So student should understand whatever their efforts they are making, they should lead to one of at least one of these criteria for getting it naturally accepted by the industry. Now there are certain suggestions which I would like to propose to the students or faculties. Basically, students they should understand that fundamentals are very important. So whatever your teachers they are teaching you, you should follow it religiously. These are important things they have seen, they have gone through it, and if you understand fundamentals, then it is easy to uh, get through many of the uh, hurdles which you come across when you go into the industry. Then at least learn one computer programming language, be it MATLAB, C, C Sharp, Python, Fortran, Java, anything. At least one programming language is must, because this will help you in the long run. Long run, know at least one open source software for programming and analysis. Then before starting any analysis, study the problem very well. apply boundary conditions properly, considering the physics of the problem. Next is benchmarking and validation is very, very important. You need to do some preliminary studies with similar problems to understand whatever you are meshing or boundary conditions, though whatever you have applied, that should be that is correct. Then report whatever. When you make the report, don't just add number of pages. That doesn't make any sense. Report should be simple, and presentation should be very of high quality. Report should like uh, ensure that what is your contribution you have made, whether you have understood the concept clearly, whether you have gone through the you have gone through systematic way. So that should include there should be many flowcharts, diagrams, figures, graphs, rather than tables and data. So if you present it in a graphical way, uh, person reading the report will be very, for him it will be very easy to understand. Then many people think that R&D, I want to work in the R&D department or in the design department. But what I would like to also highlight, that production department is also very equally important, because whatever design you make, whatever product you make, if it is not productionable or manufacturable, then nobody is going to accept it. And the person who is working in the production has a high say in the decision making. If he says he cannot make, then management will also not accept the design very easily. So don't think that only R&D or design is a very good job. If you learn directly on the shop floor, that will give more confidence and understanding, rather than simulating or doing the experiment, doing the analysis on the computer. So that is also important. You have to visit the shop floor and get the actual feel of the product, how it was, how you can measure different parameters, etc. So this is the I think I came to the end of the presentation now. So if you have any queries, you can just let me know. I'm happy. I'll be happy to answer those queries.
I'd like to request participants to ask questions, and in the chat box, please share your feedback as it has been requested by our expert. I can see some of the participants had already shared their feedback. The rest can also do the same. And from my side, I'll say it was a very interesting session, sir.
Thank you so much.
Although you may also agree that for generating all those data, the academics behind it is again very important, as because being academician, people work on that, and penetrating that is again a very important thing, and which takes a lot of effort.
Pardon me, sir.
I just tried to communicate. We have seen so many applications of the CFD.
Yeah.
But if we see academic side, the theoretical side, where we need to deal with all of equations, so many methods, so many phases. So again, getting that is again a very important thing.
Yes, that's correct. First, we need to understand the theoretical background, theoretical understanding. Then only we go for applications.
And this is my personal opinion that it was a very good session, sir, because I guess all of the participants enjoyed it. As you can see the comments also in the chat.
Thank you so much, sir. Thank you so much.
So, any questions from the participants?
Analyzing the problems.
Okay, but sir, we can't ANSYS software for create a geometry?
ANSYS, they have this PESCLAM module that is used for the creation of the geometry.
Oh, okay, okay. Thank you, sir.
Yeah.
Fine. Any other questions?
Hello, sir.
Yeah. See, in the ANSYS Fluent, or you can import the geometry in from the current software like SolidWorks or CATIA, and then generate the mesh, and then that mesh is imported in the Fluent or CFX software. So there is a option available where you can import the geometry for creating the mesh in the ANSYS. Okay.